So my name is Eddie Rowe, and I'll be the chair for today's Large System Working Group session. Welcome to the Large System Working Group stream, and this is session 9Q. On this session, we're pleased to be joined by Rob Scott from Rocket Software, who's going to be taking us through the presentation, Secure Engineering, how to develop authorized code without compromising zOS system integrity. If there are any questions throughout the presentation, please place these in the chat. You'll be able to unmute at the end to ask questions directly to the speaker. Final thing before we get started, please provide feedback. You can do this via the Bring Your Own Agenda section on the GSE website, and there should be a link there to access the feedback. This way we can improve the sessions for you. Now I will pass it over to Rob to take us through the session. So the stage is yours.
Okay, thank you very much. Okay, so I've been giving this presentation for a good few years now. When I first started doing it, I think secure engineering and pen testing wasn't quite as well known as it is now. I think there's been activity in this space. There's been press, there's been attacks, there's been successful breaches and all that sort of stuff. There are actually more tools to help a site now to protect themselves from malicious attacks. But a lot of this, our exposures probably date back to some software, internal software, ISV software that was written, in the early days, 70s and 80s and 90s, before zOS was connected to the internet, where you had a closed network, and we didn't pay as much attention to this sort of thing back in those days. So hopefully now, as the world becomes more aware of this sort of things, secure engineering is more at the forefront of what people are thinking about. So I'm just going to go through what I consider to be secure engineering. A little bit of background about storage protection in zOS, because you've got to really understand that to realize quite how severe some of the bad practices that are out there could affect you. We'll talk about the main battleground of secure engineering and what system software vendors like IBM and Rocket and Broadcom, what we have to worry about when we are authoring system software for you guys that has to do something more above what a normal problem state user can do. We'll take you through some examples of some poor design that I've seen out there in the wild. And then we'll cover some more defensive programming techniques, sort of things that if you're writing this sort of code, things to keep in mind, things to help you prevent you being the cause of a breach. Okay, so what is secure engineering? The first two bullet points here are the official definition. So it's a methodology that protects overall system integrity, and its goal is to prevent unauthorized users from circumventing and disable protection mechanisms within the operating system. That could be some sort of security system. It could be getting control in an authorized state that's beyond and above their normal authority of a general purpose user. I might be bypassing operating system memory store and fetch protection techniques. Okay. So that's the idea behind secure engineering. But I also think that, as far as I'm concerned, it also includes coding practices that prevent system down situations caused by poor techniques, by poor design, things like that. So I think it's very important that not only do we recognize the risks of threats to secure engineering, but people who are writing that sort of code are aware of the implications of the techniques that they're using. It's not an easy thing to do, to completely write a totally secure client-server authorized service providing piece of software. And you have to think of a lot of things. Okay, so storage protection. Okay, this is a little bit low level, but we have to go through this. So every 4K frame of potential storage, real storage, has a key value between 0 and F associated with it, and this is known as the storage protect key. Storage protect keys from 0 through to 7 are reserved for the operating system itself and major subsystem components and other authorized software providers. Storage protect keys 8 through F are for your normal user programs, and we pretty much only use 8 for most people, and there's 9 for kids as well. So we only pretty much use 2 of the user mode storage protected. So when a request comes in to modify the contents of storage, the key associated with the request is compared to the storage protect key of the real frame that it's trying to alter. And if the keys match, then the modification can proceed, or if the requester key is 0. And 0 in this case means zOS itself, it means the operating system. And that's very, very important to remember that, because that comes into play a lot in some of the bad practices that we're going to see. If the keys don't match or the requester isn't running 0, the request is rejected, and you will get some sort of protection exception, and that might visualize back to you as an OC4 reason code 4 event. When a request is made to read contents of storage, so we're just trying to have a look what's on that in that virtual storage. That request is normally satisfied unless the frame, the real storage frame, has a special bit on it, which is the fetch protection bit. And that says that the system is going to use the storage protect key in the same way, but just for read. So you've either got to match the key or you've got to be running key 0. And it's important to realize that the storage protect keys aren't hierarchical. So 0 is the operating system, that's your God mode. Then you've got 1, 2, 3, 4, 5, 6, 7. 2 doesn't automatically get access to 3, 4, 5, or 6. Okay, the keys have to match exactly or be 0 for the access to be granted. Typically, the requested key is taken from the executing PSW, but certain supervisor state instructions and services can pass the value in a register. The operating system knows what to do with that. So, good news is that normal user programs, they run key 8, they cannot modify the storage of things like system control blocks because of storage protection. And that, is known pretty much as a good thing. Okay, you don't want your bog standard COBOL program to be able to overwrite the contents of something like the CBT and bring the whole system. That's a good thing. Software components provided by IBM or ISV software, sometimes, and we need to provide services to normal user programs that require some sort of non-problem state authority. Even getting things like some virtual storage. If you do a storage obtain or a get main, okay, that is going to involve your user program calling a system service in order to satisfy that request. And that system service is probably going to have to mess around inside of control blocks that are not in here. We're going to flip some bits on, we're going to create control blocks in LSQA, they're going to change some P0 control blocks. Okay, so that is something that software providers have to think about when they are providing those services. So work is carried out by that authorized service on behalf of that calling bog standard Joe Schmo PA program, and then we might have to return some sort of response back to that guy. Maybe it's a return code, or maybe sometimes it's to return some actual answer data in a user provided buffer. Okay, so we have the concept of reading what we use. The authorized service has to read what the caller wanted us to do, and then return perhaps a response back to him in a buffer that he provided. And this is the battleground of system integrity and secure engineering, because this authorized, unauthorized caller boundaries is where it's all at. Okay, this is where we have to be absolutely really careful. Let's think about some bad practices before we go through some good stuff. And these are quite prevalent, and they used to be very prevalent back in the 80s and 90s. Hopefully they are getting a lot more rare. The number one obvious bad practice, and I've worked in, before I was at Rocket, I've been at Rocket for about 20 years. Before that, I was 15 years worth of NVS systems programming at various sites. And pretty much every site I ever worked at back in the 80s and 90s had one of these, an SVC or a PC routine that granted the caller some sort of elevated authority. They're referred to as a magic SVC or orthon SVC or something like that. And no matter what, when you talk to the techs, they're, oh yeah, but you need to pass, it's secure, it's great. you need to pass a special value that only we know, because we wrote it in the systems programming team and we use it for the things that we do. And we've got this special secret value. And half the time you find out that that secret value is something like 8 or 0, and you have to stick it in a register or something like that. You know, it's ridiculous. Or they might say, oh, well, you need to know the number of the SVC, so that's secret as well. But obviously, these days with smart hackers, that's a fallacy. That's very easy. Or they might say, oh, it's got some sort of internal validation of the caller. But all that sort of stuff could be circumvented with a smart enough hacker. So obviously, do not use anything like that. And if you have one of these things, you really need at your site to instigate its removal. Other bad practices, storing passwords in clear text inside storage, that goes without saying. Other bad practices I've seen throughout the years, turning on bits in control blocks to dynamically change the authority of your running work, so flipping JSCB auth or JSCB pass, or thinking that you're smart enough to start flipping bits inside your ACE control block, which describes your user identity to turn you into RACF special or operations. That used to be quite common as well. Luckily now, 2.4 onwards, IBM RACF now have a method to monitor when an ACE gets modified. So if you try doing that now, you'll generate logging records and messages on the system, things like that. Excuses that I've seen include, oh, but we only do it for a short time, or oh, we do it because we want to make the installation of the software easier. These are really bad practices now. And again, if you're doing this sort of stuff in your own code, or you have a vendor that's providing code that does this, you really need to get off that as soon as possible. Here's another bad practice that I've seen as well. And again, going back to maybe some more of the homegrown software or public domain software that you see out in the wild. You've got some sort of unauthorized caller. He'll load a module into storage, and then he'll anchor it somewhere in a control block. And maybe that's in unauthorized storage as well. And then he'll do something. He'll invoke an authorized service, maybe via auth TSO, auth program, auth TSF, that sort of entries in Palmlib. And then that will branch to that address. You'll locate that control block and branch to the EPA that the unauthorized caller set up. So that's obviously really, really bad, because any key guy can alter that memory contents and change what happens when that branch occurs. Okay, and the excuses here we see, it was deemed too expensive to redesign the code, or again, only we know the discovery logic for the control block, which is it's rubbish these days. You can't use that as an excuse. So again, obvious bad practice, we don't do it. The last one is a little bit of a hobby horse for me. I don't like it, but I've seen it quite a lot out there, especially in the public domain code. So using ALE serve check the AX, no. And the reason that people do this is they think, I need to go and have a look at some storage inside what I would call a foreign address space. So it's an address space that you don't own. It's not your address space. You haven't written software that's running in that address space. You're just curious about looking at something within the private storage of that space. So you look through the ASCBs, you get the ASCB for that address space, you get the S token, and then you do an ALE serve add for that S token, and you say check EAX. No, I want to unconditionally add that S token, get an ALEC for that on my PASN, and then start doing AR mode access to that private storage. Not advisable in most circumstances. It's going to, for one thing, it's going to OC4 if the source storage is paged out. The foreign address space that you're doing this to really has to be non-swappable for this to succeed. And you're not really meant to be doing it. And the fact it's not your code, it's not your address space. There are some niche circumstances where I think this is okay. And a good example of this is if I've written a piece of system software where I have a controlling address space, and I want to start some handler or allied address spaces under my control. I'll use the ASCRE service, the ASCII service, to create that address space. And then I may well, when that's successfully started, I get back the S token for that address space returned to me, and then I may well do an ALE serve add. But that's okay because it's my address space. I am in control, my code is in control, and that's okay. If you are, if you do have a program that needs to look at private storage in a foreign address space, and you absolutely must do it, and there's no other way of doing it, then the accepted way these days is to schedule an SRV into that foreign address space and get that to go and find the information out for you and pass it back to you in some sort of shared memory object or something. That's a much more reliable approach than using ALE search. Okay, I'll pause there in case there's any questions in the chat. Eddie, is there anything there? Or I'll just continue.
We've got no questions so far.
Okay, all right. So let's talk about how we protect the unauthorized caller boundary. So interfaces between unauthorized callers and the authorized service provider must behave predictably at all times. And that includes the intended interfaces and unintended interfaces as well. So you may well think that just because you put your authorized SVC or your PC routine behind some sort of EPA, some sort of API, that's the only way it's ever going to get invoked, right? So you've got this program that under the covers calls your authorized service, and everyone's, of course, is going to call your program. Well, perhaps they're not. They're going to sort of disassemble your module. They're going to look at your code expansion. They're going to say, "Oh, right, I can call that directly," and then they can take that discovery logic, try calling it directly, try passing in its own values. So not only are they going to try and exploit your interface there and call you with unexpected values, your code has to behave well and recover and protect itself, even when it's got a valid parameter list, and also, more importantly, when it's got unexpected things in its parameter list as well. So your interface, your authorized service, has got to correctly deal with all caller supplied storage, all caller supplied values, and, in quotes, caller supplied system control block. We'll go into that a little bit more detail. That's in quote. So you've also got to protect the resources that your authorized service deals with. So you're avoiding sharing authorized data with unauthorized concurrent tasks. You've got to serialize access to shared resources, and you've got to do separation and protection of caller data between that task that's dealing with it and other tasks as well. So there's a lot of isolation implications of what they're doing. So let's have a think about how we deal with caller supplied storage, because obviously, the caller is going to come to you with some sort of parameter list, and he might have some options, some verbs, some input buffers, some output buffers, and you have to safely deal with that. It is not acceptable to switch yourself into key 0, supervisor state, and then start moving things around with the move instruction. That is just not good engineering principles, and you are going to cause problems. Okay, so you should be reading from your caller using the execution key of your caller. You should be writing back to your caller supplied storage using the execution key of your caller. Okay? So that means that you cannot overwrite storage that is not in that caller key. So, if, for example, let's say the caller mistakenly or intentionally passed you a JES2 control block address, and you put yourself into key 0 and started moving things around and writing stuff back, you could very well just end up writing all over one of JES's most crucial control blocks in the whole system. So these are the instructions that you use. MVCPK and MVCSK, that's personally the ones that I use. There's MVCK. You can, if you're in an SVC, you can mode set to the caller's key. And there's also MVCP and MVCS as well. If you need to find out what your caller's key is, you can extract that from the stack. So if you're a stacking PC, you can inquire from the stack, what's my PSW for my caller, and then you just mask out and shift and get the caller key in a format that's recognized by these instructions and any subsequent system serve. There's a code extract there of how you might do. Personally, I have all this stuff behind convenience macros inside mine. Okay, so dealing with the caller supply storage again, as I said before, when he calls you, he's going to have some sort of parameter list. You know, it's your parameter list, whatever. The first thing you do is take a copy of that parameter list and stick it into your own authorized working storage. And again, you're going to use move with source key in order to do that. So you make sure that if the whole parameter list is in the key of your caller, and then you can start looking at the other bits inside that parameter list, ensuring that it's not changing from under you. Okay, so you need to do that as soon as you can once that your service gets involved to stop the caller or an allied subtask inside the caller address space changing those contents without your knowledge. So what I would probably do here, if I was providing some authorized code, is I would have some recovery routine established right at the beginning of my PC routine that covers all accesses, all storage afterwards. And during that initial validation phase, you're probably going to gracefully terminate in case the user's provided you something wrong. So he's given you zeros instead of a valid address, or he's given you like the wrong key, or he's got the eye catcher wrong, or the length wrong, something like that. You can, in your recovery routine, you can gracefully recover without a SVC dump, give a bad return code, you know, a bad parameter list of style, return and reason code, and then re-establish more traditional recovery afterwards, where you might want to take an SVC dump for a more serious logic problem that might occur later. Writing to caller supplied storage. Again, remembering what we said earlier, write back in the key that the caller was executing in. And there's a lovely instruction there, NVCDK. So what we've done at Rocket, various products, we have services and macros that basically go in front of, you generate MVCDKs. So we can do the equivalent of a move long with destination key. So we can move as much storage as we like back to the caller, and it just basically does an MVCDK loop. So we know it's a secure way of writing back to your caller. Again, no real exceptions here. You should only be writing back to caller supply storage in the key of caller. And again, do not think I'm going to go into key 0 and do it because it's easy. Right? I can get it to work. Of course, you can get it to work, but that's a really, really poor program. Dealing with caller supplied values, so the values the caller gives to you. But the rule number 1, don't trust it, and rule number 2, see rule number 1. You cannot trust anything that your caller gives to you. And I'm not talking here about your API load module. I'm talking about your SVC or your PC routine. Okay, the guy that's actually going to get control and all that stuff. So you have got to do some really, really basic things. Verifying any values are legitimate. You've got to check for your boundary conditions. You've got to check for 0, null, negative, too small, too large. Okay. And I know some programs in the past have skipped this because they were too lazy. But this is why you have buffer overflow problems in various pieces of software. And if you don't do this, unexpected things can happen, and you will be at fault, and your code will go off the rails, you know, and do something weird. And debugging it will also be difficult. Check values for consistency. So if they provided this guy, make sure that the other guy, the allied value, is the same. But you can't rely, again, going back, you can't rely on your interface layer to do this. You have to do this in the authorized code as well. And obviously, any other additional values that are specified in a subparameter list, you've got to do the same. You've got to take a copy into authorized working storage before you reference it, again, to stop them changing in flight. Okay, dealing with caller supplied system control blocks. Well, the general rule here, you don't. All right, you do not accept them across the authorized and unauthorized caller boundary. So if there is a system control block to locate, you've got to locate it for yourself in your authorized code from trusted sources. So if it's an IBM control block, you've got to go and get it. If it's your own control block, okay, go and find it from trusted sources. Don't trust control block addresses given to you by an unauthorized caller. Okay? So many problems I've seen in this area do deal with things like that. And even when you have got a control block being passed between two authorized callers, and that's valid inside a piece of system software, you would still be highly advised to do eye catcher verifications, version number checking, length checking, sanity checks just between the two, because I've seen a lot of problems called in system software, maybe during the development stage, but called because they've got a parameter list that is invalid. And so it's always worth doing a belt and braces approach to control them. Okay, so let's go through. I'll stop here in case there's any other questions. I don't see anything in the chat. Eddie, I assume we're still fairly free.
Yeah, there's still nothing in the chat.
All right. So let's go through some examples of poor design. So I've sort of said, these are all the things you've got to do. So let's see what you shouldn't do. And these are things I've actually seen in the wild as well. I've obfuscated some of it a little bit. But here's a common thing. Okay, so they've got a piece of client code. It locates its product server anchor as some sort of control block in ECSA. Maybe they've hung it off of the SSCT, or maybe they've got a named token or something like that. So then the caller then builds a parameter list requesting a function for the client user ID. So he's got his palm list desect here, he's got an eye catcher, he's got a function code, he's got the user ID of him, he's got the anchor block address that he's found, he's got an answer area pointer where he wants the results to be put into, and then he's specified what his answer area buffer is. Okay, so he's got some logic inside the client code that locates the PC number from the product anchor and passes the address of this parameter list via R1. The PC routine is defined to run P0, as a lot of software products are, and it accepts the parameter values, established addressability of this control block, address passed in the anchor field, and branches to a SAT security check module whose EPA is off that product anchor block, and passes the user ID to validate the caller's authority to use the function code. Now, I've seen code like this out in the wild. I've seen it, on CPT tape sort of style, public domain as well, and I've seen it at sites where someone has come along and they've written a bit of code and it's been running there. There's at least 3 major secure engineering design flaws inside this little bit of scenario, and we'll just go through them. Okay, so palm list is referencing key 0 and not in the caller's key. So you've got to make a safe copy of palm list. So it can't change it after reuse. And again, you've got to use MVCSK to take the copy in the caller's key. The PC routine has faithfully and trustedly used the anchor address passed by the client caller. So this could be spoofed to make it look like the real thing. You could stick it in a bit of P8 storage. You could initialize the eye catcher properly, and then you could put your own entry point addresses in places where that authorized service can branch to. So again, always locate system control blocks and your own control blocks from trusted sources. And again, the PC routine branches to a module using the EPA stored in an untrusted anchor block, so the caller can wall the security check. The caller can cause an authorized routine to branch to the caller's own routine in memory. Thereby, you can elevate the caller's authority. You can then start turning on his ACE bits, or you can turn on JSCD auth, and then you can start running authorized code and bypassing all your protections. And also, the other thing is the PC routine passes the user ID from the caller to the security check. I mean, that's ridiculous, right? You could say, I'm IBM user, or I am root, or whatever. So obviously, again, when you're doing identity discovery, there are ways that your authorized code can find out user ID of your caller. Okay, number 2, there's only 2. Okay, so later on in this poorly written PC routine, it's time to copy some data back to the caller with the address passed in answer area in that palm list desect. The address of the data to be returned is in authorized working storage field inside WA answer area, and its size is in WA ANSS. So he's done some logic inside the piece of routine. He's got the answer area of the buffer he wants to return. He's got its length because he's nicely kept track of it while he's been gathering the data, and now he's going to copy it. So what he's doing here, he's saying, right, okay, I'm gonna get the caller's answer area. I'm going to get the address of my answer area and its length, and then I'm going to do an MVC out and copy it straight back. There's a couple of really major flaws here. Piece routine again is running in key 0, and the code unconditionally writes back to the caller storage without using the call key. But also, and more seriously perhaps, the code unconditionally writes using the length of the source data without any validation of the caller storage length. So you could provide an overwrite here, so you can start writing over and past the caller supply buffer. Okay, so those are sort of things to avoid. So let's have a think about good things, good techniques, and what I call defensive programming. And I really believe in defensive programming because it means I get less APARs on my software. It means I don't get called out of bed in the middle of the night because I've caused some serious problem. Because I've done some serious sanity checks on anything I get from my call. And the first thing I'm going to say is executing in key 0 should terrify you. It should terrify every single software engineer that writes authorized code, because you're just one instruction or one wild branch away from causing an unscheduled IPL for your customer. And also, storage overlay problems are one of the hardest to debug. Overwriting a single byte of hex zeros can bring your system down, and it's very, very difficult to locate how that happened. It's not as if every single storage overlay you put your entire company copyright statement all over the CVT. It's not as easy as that. It could just be hexFF, it could be 00, or you could just overwrite something by single byte or word, and that can cause a really serious problem. And quite often, and we have found this a lot, it's not your mainline code that causes the overlay. Okay? It'll be an infrequent logic path within your code that doesn't get exercised so much at your site or most customer sites, going down an infrequent path, or you've taken some sort of weird error, some sort of recovery error, and then you end up going somewhere where you didn't expect. And the other thing is, if you are running software that's running in key 0, every time there's a system down because we think there's been an overlay, your software is under suspicion. I mean, you cannot be given a no blame blessing, okay, because you are running in key 0, so it could be you. Okay? So what I say is every developer should suffer from what I call key 0 anxiety. Okay, I suffer from it all the time. I'm not good enough to write in key 0 all the time. I'm not Peter Elson. So how do I get over key 0 anxiety? Right. So the most obvious thing is don't have your code, authorized code, running in key 0. Use an entry in the NBS PPT to declare your server object program to another key. And this is what we do at Rocket for a lot of products. We will have a key that we use that's not, it's between the ranges of 0 and 7, and we will run in that key, so we won't run. So here are the sort of well-known non-problem state execution keys. So 0, as I said before, is the BCP. 1 is JES, APPC, and some aspects of TSO. 2 and 4 are pretty much unused these days. There were some components that used them a long time ago, but pretty much these days they're unused. And what you'll find is ISVs will use one of those two values. Okay, so you've got I personally use key 4, so SGSF executes in key 4 on the server side. We've got other software products at Rocket, and there's Broadcom products I know of that run key 2 and key 4. Key 5 is data management, DFPs. That's all your data set stuff. 6 are VTAM, and 7 for DB2, MQ, and IM. And this is what a shared XX member syntax would look like for your program, your server program. PPT, program name, blah, 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 and what key it's going to run in, and you're probably going to want no swap as well because you're supplying system service. If you actually write software for IBM, which I do, they can add your JobStep program in the default PPT that comes up with zOS. So I don't even have to have instructions on the install of SUSF to say, oh, you must remember to update the PPT with its server program names done for me by the guys over in Fixit. That's really nice. Also, things to remember, a lot of developers back in sort of like the 70s, 80s, 90s thought that, oh, I'm calling a system service, I need to be key zero because I'm calling an authorized service. Well, these days, most authorized services execute in all non-problem state keys, and that's really great because if you're running key 4, like I am, or key 2, okay, the last thing you want to do is frequently switch to key 0 because every time you're in key 0, you are one instruction away from calling an unscheduled IPL. So, the more I can stay executing in key 4, and I think, in my code, there's a tiny little spot where I have to go into key 0 because you have to be key 0 for a specific IBM service. But 99.999% of the time, I'm running key 4, and that makes me feel very, very happy. I have seen software out there where the developers have decided to run their server software key 8, and then they switch keys to key 0 before doing their authorized bit. I know that they do that. I'm not a fan. I think it's fraught with risk. I think that it's difficult to safely communicate a server between key 8 and key 0 sections of code. Recovery is tricky. Memory management is tricky. I wouldn't want to do it that way. If, as I said here, if you're running key 2, key 4, you don't have to keep switching keys, which makes everything much, much easier. PC routines can run key 2, key 4. SRBs can run key 2, key 4. You can have key 2, key 4 common storage, and you cannot overlay. If you're running key 2 or key 4, you cannot overlay key 0 storage. So I am never going to overlay an IBM system control block. Another thing that we can think about, storage management and memory management comes into secure engineering a lot, is subpools. The subpools, some subpools are sensitive to the key specified on storage obtain, get main, and some are not. And you get TCP key, and the service is completely silent about it. So if you call get main storage obtain for a subpool, and you say, well, I'm going to specify the key because I want it in this specific key, use my subpool number, but that subpool doesn't support key selection and just gives you back in TCP key, it's going to work, but you'll get it back in the wrong key. So consider the following example. So you've got a PC routine with a client caller in key 8. The PC routine executes in key 0, uses some generic prologue macro that gets its working storage, who has a default subpool of maybe some like 50. And the developer thinks, oh yeah, it's great, it works, fantastic. I've got key 8 storage, key 0 storage in that subpool, but they're not, because it's a PC space switch. So we've gone back to the TCP key of the caller, which is 8. So what's actually happened is that the code has in fact obtained and used key 8 storage for its work area. But of course, the code has worked because we're key 0 and we're just overlaying on top of that. Okay. So again, there are other subpools that you can specify that would have been a better choice. They do use the key specification on storage obtain and get main, and they use the thread. So as I said, what we use for this specific example is something like subpool 229 or 230, and it's all documented in the MVS diagnosis. Got sensitive data, then use fetch protection. So you do have something sensitive. You can specify that you want to have fetch protection to make sure that problem set callers cannot browse that storage. And another tip that I always give people, don't use subpool 0 for anything, even in unauthorized code. Because it's just the general bucket of where every Charlie puts its storage. Okay, so if that address space starts to leak storage somehow, leaking memory. If you're in there with the world and its wife in subfield 0, it's difficult to know if it's you or not. It's difficult to debug using IPCS VSM list or other tools, online tools that can look at subfields. So I always advise that developers come up with, you have a range of 0 to 127 that share all the same attributes as subfield 0. Use specific numbers in there because it's much easier to debug your problems and also QA your problems, because you can run your servers or your clients for a long period of time in QA and then just check the storage stats in that specific sub. Some good practices. Clear storage when the system doesn't do it for you. So there are some rules about when the storage is given back to you, cleared, about whether it's storage boundary aligned, size it is. Sometimes the system will clear it for you. Sometimes you'll get it cleared by accident, and sometimes it's not cleared. And this is another problem for software developers as well, because if they're testing their software on a low use system, it could well be that while during that testing they are getting clean buffers back all the time. Okay, but they shouldn't be, because they're not obeying the rules on storage obtain, get main, and they should not necessarily be getting that back clear to 0. So there's a lovely keyword on the storage obtain called check 0 yes, and it tells you whether or not the system has cleared that storage for you. So you can avoid initializing it yourself when you know the system by that return code has done it for you, which is really good. Again, as I mentioned earlier, eye catchers in control blocks are really cool, really good. Use them, use version numbers, change the version numbers when your lengths change, all that sort of stuff. It's just good practice to have sanity checks inside your code to make sure you don't trust them. I've seen lots of code where they've got a complex control block structure and they've got no eye catchers, there's no version number, there's nothing, there's just data, there's just addresses and bits and things like that. I just don't know how those guys sleep at night, because it must be so hard to try and debug and verify software. Always assert your length checks. That's another thing as well. If you've got fixed sizes of things like work areas and buffers and stuff like that, it's very easy for a developer to come along later on and add new fields into that block and then exceed the length that you think it should be. So you can write yourself like assertion style macro statements and sort of say, this length of this structure must never exceed this number. And if it does, I'm going to flag it as a compile or assembly error. If you have fixed offsets that must be fixed by architecture, maybe you've got stub modules that rely on finding things at certain offsets, assert that in your code as well. So you have, again, a way of fading the assembler or the compile if that offset changes for whatever reason. If you are a PC routine developer, there's a lovely latent parameter area in the etdef that you can pass product-specific information. So, for example, if you've got maybe a multiple server environment, you have multiple instances of your software where it would be awkward to try and locate the correct anchor block in every time from scratch. You can, while you're setting your PC routines up, you can pass your anchor block address in a trusted way via the latent parameter area of the etdef, so that when your PC routines get control, the latent parameter area is passed on R4 on entry to your PC. So that's a really nice way of doing your trusted location. Explicitly clearing memory to hold sensitive data, of course. Someone might be running a debugger, someone might see the data in an SVC dump. And there's another one that's come in recently, which I also like. Executable equals no for storage obtained for data structures. Okay, so we have gone to complete executable no for all our buffers wherever possible. And if you are a system software author, you should be running a couple of things. There's these diag_xx traps that you can specify in palmlib, where you can get the system to deliberately dirty the storage that you get back on get main and storage obtained if it doesn't adhere to those rules that we mentioned earlier. There's also another service that's called Prime PSA that can dynamically update low storage, patch lazy references and page zero references it in your code that they're getting away with it at the moment because it just so happens to be zero inside that byte in PSA. Prime PSA can change that on the fly, every few seconds or so, and it'll catch it. That's a really good thing to do. And as I said earlier, think beyond the API that your software provides. So malicious users will bypass your expected environment. Your PC routine discovery logic that's tucked away inside your API, that's not hidden from anyone these days. This is an example exposure that I have actually seen in the real world due to length issues. So there's some code, and the version 1 of this code obtains some CSA to hold some structures and to enable an SRB to be scheduled to another address space. And the overall size was something like 4,200 bytes. This size is greater than 4K CSA. zOS returns the CSA initialized to hex zeros. So the developer never cleared the storage. He just formatted it correctly, and it included the space for an old SRB control block. This is before IEA mentioned. And the code runs fine for months/years. Then the developer changed the code slightly, and that actually reduced the size of this block to around about 4,000 bytes. Okay? Code runs fine on the test LPAR and is released to customers. At a customer site on a high workload system, the target address space of the SRB is fatally impacted and just goes into an awful state, and pretty much brings their whole production system down. And what had actually happened under the covers was the new smaller size meant that zOS did not initialize the storage to zeros on a busy system, and it just so happened that one of the bytes that was initialized to zero was inside this SRB control block, and it meant something that was disastrous. So the dirty bits called fatal damage to the target address space. And it just so happened to be, as I said, a production online multi-user address space. And the reason I know this is that I was the developer, and this was back in my 20s. And to this day, it still gives me chills to think how bad that was, and how awful I feel about it. And of course, it would have been completely avoided, if I'd had some sort of a cert on the side of the control block, and if I'd used check zero, so that I would make sure that software had been initialized to zeros. So you'll learn from some of your worst mistakes. There are some miscellaneous gotchas. So, first one, R13 always points to a save area, right? No, it doesn't. Not in a eStay with no SDWA. Also an FRR, also an SRB. So, always know your entry regs. Another one that I've seen a lot, macro usage in the incorrect environment. So you've got some macro that's been used in your product or other products, or it's a common macro, but no one's ever used it before in a piece of authorized code, and you just used it. No one's used it before in cross-memory mode or AR mode. And there's nothing in the macro to do any sort of environmental checks during the use. Another classic here is making every load module AC1 in your APF authorized load library. And this is the thing I've seen, especially back in the 80s and 90s. I've got an APF library, everything in it needs to be AC1. Or I'm calling this program AC1, so everything it calls has to be AC1 as well. Only job step programs, except program equals in the JCL, need to be linked AC1. And what we're finding now is that hackers are taking other AC1 programs supplied in a APF authorized library and putting them on the exec program equal statements and passing a palm to them to see what happens. Okay. Maybe it'll abend, and most of them do, but it has sometimes they cause damage, sometimes they actually branch back to areas within the palm string. And so a smart hacker could put hexadecimal inside that palm equals quotes, and maybe even pass control to a previously loaded piece of storage and elevate their authority. And it sounds ridiculous and it sounds unlikely, but I've actually seen it. And the other gotcha, of course, is copying code without really understanding it, just because it works. To know as well. So here's some help and references for you. I did a session back in SharePoint Work in 2020 called the zOS cross-memory server code walkthrough. So that was some sample structured assembler code for both problem state client and an authorized server started task. So I did this because I realized that there was no really good example out there. If you look at all the IBM manuals, they have little code fragments, but no one has ever sort of said, well, this is how you do it from soup to nuts. This is what you do. And I've seen many, many poor examples of authorized code in the public domain. So I wrote this to try and help people use a good starting point. So it sets up a reusable system LX, it sets up a piece of space switch, it uses IEAM shared to send SRVs. It's got some examples of how you might PLO serialize a request queue. It's got 64 cell-put buffers. It's got MVC, SK, DK to transfer the data between client and server. And if you want to go and have a sniff at it, it's on GitHub. It's in a style that some people might not like because I use structured macros, but I think the concepts are still good, and I think it's still a good example. Some references. Carl Schmitz, who's now retired, he used to do all this talks around various sites in the old days. zOS system integrity, authorized software without security holes, and there's obviously the various authorized assembly services guide, and then there's the MVS planning and security manual as well. And I suppose my biggest help here is my own personal battle scars. I've been writing authorized code for about 35 years now. When I think back to some of my attempts in my 20s, it makes me shudder. But I think I've learned a lot over the last few years, and that's why I'm trying to share it with you guys. Okay, that's the end. I'm happy to answer any questions. You can unmute and chat away, or I'll let you go to your next section.
Great, thank you, Rob. So please all, if you have any questions, feel free to ask them in the chat, or you should be able to unmute and ask them now as well. Okay,
don't look like we've got any, Eddie. So time to wrap it up, I think.
Great. So if no more questions, then I'd like to say thank you for everyone for attending the Large System Working Group stream. This is session 9Q. And a reminder to please give feedback when you go to the Bring Your Own Agenda section. And thank you very much for attending this session.
See you, everyone. Bye-bye.